Let's look at the idea of vector proofs. And that's the idea that we use vectors to argue for a particular proposition, right? Or to prove a statement. We want to prove a statement is true. We want to establish an argument using vectors. In this case, this is why it's vector proof. And we want to use that to reach a conclusion that supports the proposition and supports the claim. So let's start with the triangle OAB. M is the midpoint of its base AB. So here's the line AB. M is its midpoint, triangle OAB. Okay, this vector on the side here is the vector A, OA. We represent as the vector lowercase a with a tilde. OB is the vector B, lowercase b. I want to prove that if the triangle OAB is isosceles, so if OAB is isosceles, that's two opposite sides equal and the two opposite angles equal, two base angles equal, with OA equal to OB, then we're claiming that the line OM down the middle here is perpendicular or at right angles to the line AB across the bottom, the baseline. All right, and for that, the vector OA will be represented as lowercase a with a tilde under, and the vector OB with lowercase b. All right, so we want to argue that if M is the midpoint of an isosceles triangle, then the vector OM, or the line OM, is perpendicular to the line AB. All right, and we'll be arguing that's true for all isosceles triangles. Okay, well, let's start then. We've given that the line OA is equal to, that OA, the length there, is equal to OB because it's an isosceles. We want to prove that the line OM is perpendicular to the line AB. All right, now we've got, to begin with, we're given that OA is equal to OB, so because we're told it's isosceles. And OA, okay, this here, we can represent the magnitude squared of OA is just going to be A dot A. Because you remember we've got OA is equal to A, and so the magnitude of OA, okay, will be, and the square of that is simply going to be A dot A. Because remember the magnitude of OA is just the square root of A dotted with A, and so the square of it is just remove the square root. Okay, similarly with OB, okay, the magnitude squared of the vector OB is simply B dot B. All right, and if we look at the diagram here, we can see that OM could be made by the addition of the vectors OB plus OA, okay, and then halve that result. So if I took the vector OA and I added OB to it, that would be something like that, then the resultant vector here, okay, that would be A plus B, all right, and then we just want half of that length, okay, halfway through there, and so we put the factor of a half out front, okay. Next bit then, so we have OM is a half little a plus little b with the tildes under those vectors, and that AB, we could make an argument for OAB, the vector AB across here, as being OB minus OA. So if I can just go off to the side here, if I've got OB like that, and then I add on the negative of OA, okay, negative OA, and this is OB, then the resultant will be across here, okay, and that will give me AB, okay, like that. A little bit crunched up there. So AB, the vector AB, is OB minus OA. I hope that's okay, everyone. And we can represent OB, of course, by lowercase b with a tilde minus lowercase a with a tilde. All right. So now we've got AB, we've got OM, and just looking at the diagram here, AB, OM, okay, we want to argue they're perpendicular. Okay, well, let's put in our expressions. So OM dotted with AB, well, OM is this one here, and AB is this one here. Okay, let's expand across the parentheses so that we have A dot B, right, minus A dot A, plus B dot B, plus B dot minus A, so we get negative B dot A. Okay, now these terms cancel, right, and we're left with, in the parentheses, B dot B minus A dot A. Okay, now B dot B, A dot A, we've already discovered that they're actually equal. And so they sum to 0. If I go back up here, we should see that A dot A and B dot B, if we look up here, okay, they're equal. And so that cancels to 0. Okay, well, if OM dotted with AB is 0, that means they must be perpendicular, given that OM is not 0 and AB is clearly not 0. So that means that OM is perpendicular to AB. And coming back to the diagram, that means that OM here, okay, is perpendicular to AB here. All right, so we've established our first result. All right, let's have a look at another example. Okay, here's another example. We've got the triangle ABC. Okay, P is the midpoint of CA, and Q is the midpoint of AB. Okay, notice we've written it C to A, hence the arrow is pointing this way. Okay, we want a vector that goes from C to A, and here Q is the midpoint of A to B. So we want a vector that goes from A to B, and that's why the arrow points this way. Okay, now we're setting AQ. Okay, what we're saying is that C to A, right, is the vector A, and AB is the vector B. All right, then AQ will be half of B, since Q is the midpoint of AB and P is the midpoint of CA, so we're taking P to A as half A, all right? A to Q is a half B. And we want to prove that PQ is parallel to CB. PQ is parallel to CB. Okay, so this line here, we want to prove is parallel to this one. And that PQ is a half CB. All right, so this length here will be a half of that. All right, well, let's start here. We've got P to Q is going to be P to A, okay, plus A to Q, and that's the same as P to Q. So if I just scroll down a little bit more, we see that a half A plus a half B will give us our P to Q. Okay, so, and we can write that, just pull out the common factor of a half outside the parentheses, we've got half A plus B. Now, CB is going to be, from the beginning here, is going to be C to B, that vector there will be CA plus AB, added sum together will give us the vector C to B. But the thing is, we know that that's the same as 2 times P to A plus 2 times A to Q, because remember that length there is the same as that length there, so A to Q is the same as Q to B because Q is the midpoint. And similarly here, C to A, the midpoint is P, so C to P is the same length as P to A. Okay, so let's come back here, and we have 2 times PA plus 2 times AQ, so 2 times a half A plus 2 times a half B. So that gives us then that CB is A plus B. Okay, Now CB is A plus B, so that PQ is a half CB. Okay, PQ, let me just show that diagram. PQ is then a half CB. All right, I think we can establish that from the proof there. All right, so that gives us that PQ is a half CB, so that's part of the problem. Now, we want to show that PQ is parallel to CB and half its length. Okay, and that's what we've managed to achieve, that PQ is half its length, it's half of CB, and so the magnitude of PQ will be a half of the magnitude of CB. Okay, and the fact that there's equality here with a scalar in front means that these two things are parallel. Remember the condition for parallel vectors? You had PQ, some vector PQ is equal to K times the vector CB, and that means that they are parallel. In this case, the constant K is a half. Okay, so PQ is a half CB, but they're also parallel. So we've established the result.